You know, when you look at the modern world, you usually just see the finished product. You drive past a massive oil refinery at night, and it looks like this incredible city of lights and steel. Or you look at a power station and you just think, electricity, it's static, it's done.
Right, it's just a permanent fixture.
Exactly. But there is a moment long before the first shovel ever hits the dirt where that billion-dollar facility is, it's nothing more than a concept, just a high-stakes idea floating around in a boardroom somewhere.
And honestly, that is the most dangerous moment in a project's life.
Really?
Oh, absolutely.
Really?
Because you have I want a refinery that produces X amount of fuel, and you have this empty, dusty plot of land.
Yeah.
But the gap between those two things, it's massive, and it's incredibly expensive.
And that gap is exactly where we are doing our deep dive today. We are looking at the bridge across that gap. It's this specific engineering phase, but as I was reading through our sources today, it felt way more like a survival guide for mega projects.
Yeah, that's a good way to put it.
It's an acronym. FEED. Front-End Engineering Design.
It really is the brain of the project. If the construction phase is the muscle, the cranes, the welding, pouring, the concrete feed is the nervous system. It's the logic and the memory. It defines what the muscle is actually supposed to do.
To help us navigate this brain, we are unpacking two pretty dense but surprisingly fascinating source documents today. We have an employer requirement feed package, specifically document E4.1, and a typical feed index, which is document EA9.
And just to clarify for everyone listening, these aren't the blueprints.
Right, not the ones you see in movies where someone unrolls a giant paper scroll on a table.
Exactly. These are the instructions for making those blueprints.
Which is wild to think about.
It is. And just to set the stakes here, if you get the feed phase wrong, it doesn't matter how good your builders are. It doesn't matter if you hire the best welders on the planet. The project will likely fail.
Wow.
It will run way over budget. It will violate local laws. Or, in the worst case scenario, it will be physically unsafe to operate.
So let's start with the acronym itself, just to ground everyone. Front-end engineering design. I'm looking at the definition right here in the employee requirement document, E4.1. It lists a ton of deliverables. Specifications, design basis, technical requirements, drawings, norms. But practically speaking, who is this actually for? Like, who is reading this massive stack of paper?
Think of it as a baton pass. That is the best way to visualize it. You have two main players in this game. First, you have the employer.
That's the company putting up the money, right?
Right, the client. They have the money and the vision. Then you have the contractor. That's usually a massive engineering firm that will actually figure out where every single pipe and bolt goes.
Okay.
FEED is the package that the employer hands over to the contractor. It says, here are the rules, here are our constraints, now go do the detailed design.
And looking at the text in document E4.1, this isn't just a casual suggestion. The document explicitly states these are the basis for contractors' detailed design.
Oh, it's actually much stronger than that. If you look closely at that section, it mentions the contract MDL, the master document list.
Right, I saw that.
Once these FEED documents are included by reference in the MDL, they become legally binding instructions. It's required for the realization and completion of the works.
So it's not just friendly advice.
Not at all. It's the legal anchor for the physical reality of the plant. If the FEED says the pipes need to withstand a certain pressure, or they have to be made of a specific metal alloy, and the contractor decides to design them differently to save a few bucks.
They are in breach of contract?
Exactly. This document is what protects the employer from getting a substandard or dangerous plant.
Which totally explains why the second document we have, the typical feed index document, EA9, is so incredibly detailed. I mean, this thing is exhaustive. It's essentially a table of contents for an encyclopedia of engineering. It covers absolutely everything.
It has to. And you have to remember, this document, EA9, is a template. The source notes specifically that it is indicative.
Right. It has all those placeholders.
Yeah, brackets for logos and project names, because it has to be reviewed and modified by the consultant after the commencement date. Every single project is unique. But the structure of it, the structure is universal. It covers everything from the dirt deep underground to the software code running the control room.
Let's actually walk through that structure because the way it's organized tells a really compelling story about how these massive things actually get built.
It does.
It starts with Part 1, general information, and Part 2, design basis. To me, this felt like setting the stage. Like, before we even talk about pipes and valve, let's talk about where we physically are.
It is setting the stage, quite literally. You can't design a machine until you know the exact environment it's going to live in.
Yeah.
That's why you see local information and meteorological and site data right at the top of the design basis.
Which sounds kind of obvious, right? Is it raining? Is it sunny? Do we really need a whole engineering dossier just for the weather?
You absolutely do, because it's much more specific than knowing if you should bring an umbrella to the site. Think about wind load. If you are building a distillation tower that is 200 feet tall, which is basically a giant metal sail, the wind speed at the very top is totally different from the ground level. If you're building in a hurricane zone, that steel needs to be much, much thicker.
Oh, right. That makes a lot of sense.
Or think about extreme temperatures. If you're in the Arctic, the liquids are going to freeze inside the pipes. If you are in the desert, your delicate electronics will overheat. Or if you're building on the coast, the salt in the ocean air will just eat away the metal.
So the design basis dictates the actual physics of the plant.
Exactly. If you get the weather wrong in the feed phase, the plant falls down or rusts away. It's that simple.
There was one item in part 2 that really caught me off guard, though. It kind of stuck out like a sore thumb. Right there in Section 5, listed right alongside serious, heavy-duty things like civil engineering and electrical engineering, is ergonomics.
I love that you picked up on that. It's
Yeah.
genuinely one of my favorite parts of modern engineering standards.
I mean, be honest. Usually when I hear the word ergonomics, I think of a fancy standing desk or maybe a comfortable mouse pad so my wrist doesn't hurt at the office. But we are talking about a massive chemical plant here. Why is human ergonomics a foundational design requirement?
It's all about human error. And more importantly, the stakes of human error. In an office building, if your ergonomics are bad, you might get carpal tunnel syndrome. In an industrial facility like this, if an operator needs to close a critical safety valve during an emergency, they need to be able to reach it quickly.
Okay, that changes the perspective entirely.
Imagine if that emergency valve is placed 7 feet high,
Oh.
or it's tucked away behind a blistering hot steam pipe, or it's at an awkward angle where the operator has to lean dangerously over a railing just to turn it.
They might hesitate.
Exactly. In a high-stress, alarm-blaring situation, they might hesitate, or they literally might not be able to apply enough physical torque to force it closed.
So ergonomics here isn't about making sure the control room chairs are soft.
Not at all. It's about pure safety and usability. It's about the interface between the fragile human body and this massive machine. If the plant isn't designed for humans to actually operate it, catastrophic accidents happen. So the feed index forces the engineers to produce an ergonomic study covering valve accessibility, control room layouts, lighting before a single pipe is ever welded.
That actually flows perfectly into part 3 of the index: regulations, standards, and specifications. This felt like the ultimate hierarchy of authority.
But rules of engagement, basically.
Right. It lists statutory regulations first, then employer standards, then national and international standards, and finally contractor standards. Is there a strict reason for that specific order?
Always. Statutory comes first because that's the literal law. Local laws, national environmental regulations. You cannot build something illegal. That's totally non-negotiable.
Right, the police will just shut you down.
Exactly. Then comes employer standards. Big global energy companies, for example, have their own massive internal rule books. And these are often much stricter than the local laws because they want all their plants around the world, whether they are building in Texas, Nigeria, or Norway, to operate exactly the same way.
So they have consistency across their whole portfolio.
Right. It allows them to move staff around the globe without having to retrain them on basic safety protocols every time.
And then national standards just fill in whatever gaps are left.
Precisely. And if you scroll down a bit in the document, you see references to design and engineering practices. This is where the feed document gets incredibly bossy.
Bossy how?
It doesn't just say build a safe concrete wall. It refers to specific codes that tell you exactly the ratio to mix the concrete, exactly how many inches apart to space the internal rebar, and exactly what grade of steel you are allowed to use. It removes all ambiguity.
Okay, so we've established the location, the human constraints, and the legal rules. Now we get into the really heavy lifting. Part 4, the design dossier. This section is just huge. It seems to cover the actual physical stuff inside the plant.
This is the absolute meat of the project. This is where those abstract requirements turn into actual physical systems.
It starts a lot with visualization, plot plans, and site plans, which makes perfect sense. Obviously, you need a map of the site. But then I saw Section 4, 1.8, hazardous area classification documents. Well, it sounds pretty ominous.
It is incredibly critical. Hazardous area classification is basically the process mapping out invisible risks. You are looking at a drawing of an empty dirt lot and mathematically calculating, if a pipe leaks right here, where will the toxic gas go?
Yeah.
How far will the invisible explosive cloud spread?
So they're literally zoning the plant based on potential explosions before they build it.
Yes. You define distinct zones. Zone 0 might be the inside of a massive storage tank where explosive gas is basically always present. Zone 1 might be the area right next to a high-pressure pump where a leak is highly likely to happen during normal operations. Zone 2 might be further away.
And why does knowing the specific zone matter so much?
Because if you are operating in a hazardous zone, you cannot use a regular light switch or a regular motor. A standard light switch creates a tiny, almost invisible electrical spark every single time you flip it.
Like the ones in your house.
Exactly. In your living room, that's perfectly fine. But in Zone 1, if you're surrounded by an invisible cloud of combustible gas, that tiny spark blows up the entire facility.
Oh, wow. So before they even buy a light bulb, they have to map out these danger zones.
They have to. It dictates every single piece of electrical equipment they are allowed to purchase. It all has to be certified as intrinsically safe or explosion-proof. And the FEED document forces you to do all that complex mapping early on.
Another thing that really stood out in Part 4 is the realization that this new mega plant doesn't just exist in a vacuum. Section 4V2 is called General Interface and Tie-ins.
Ah, yes. The dreaded tie-in.
Why dreaded? What's so bad about it?
Because a tie-in is where your shiny, new, perfect project has to meet the old, dirty, rusty reality of existing infrastructure. A tie-in is simply the physical connection point. Say you are building a new power plant, but you obviously need cooling water from the city's main water line. Or you are building a new refinery unit that has to feed its output into an existing pipeline network.
And I see tie-in location plans listed right here in the index.
You have to know exactly, literally down to the millimeter, where that physical connection is going to happen. Imagine the horror if your brand new pipe arrives at the property boundary and the existing pipe you need to connect to is 6 inches to the left.
That sounds like an expensive mistake.
Or worse, imagine the existing pipe actually operates at a completely different pressure than you assumed it did based on old paperwork.
Then you have a massive problem.
You have a catastrophe on your hands. You might have to force a shutdown of the entire existing city system just to fix it, which costs millions of dollars in lost production or fines.
Yeah.
Or you have to hurriedly re-engineer your new pipe on the fly.
So the FEED document is forcing the engineers to plan out those critical handshakes before they start digging.
It forces you to send surveyors out to measure the existing physical reality, rather than just assuming the 30-year-old blueprints are still accurate. It compels you to define every interface.
Now, let's look at the operational units themselves. The index breaks them down pretty clearly.
Yeah.
You've got process units in sections 3 through 7, power systems in section 8, which includes single-line diagrams and electrical protection diagrams, and utility systems in section 11, which is the water, the air, the support stuff.
Right.
But what I found absolutely fascinating, and maybe this is just me being a nerd about spotting patterns in data, is the repetition across all these sections.
Repetition is a core part of engineering discipline. What specific pattern did you notice?
Well, for every single unit, whether it's the highly volatile chemical core of the plant or just the basic water treatment system, I see the exact same required document listed over and over again. Process Safeguarding Flow Scheme and Safeguarding Memorandum. It's practically a mantra in the text. Safeguarding, safeguarding, safeguarding.
It really shows a systemic, almost obsessive focus on safety.
Yeah.
But it's very important to understand the technical difference between control and safeguarding, because the index lists both of them.
Yeah, I did see control narrative listed a bit later. What is the difference between the two?
Control is about making the plant actually do its job. Open this specific valve to let the raw fluid in, turn on this giant heater to boil it, turn on this pump to move it to the next tank. That's everyday operation. That is the gas pedal of the plant.
Okay, that makes sense.
Safeguarding is entirely about what happens when that control system fails. If the heater's control breaks and it doesn't stop heating and the internal pressure gets dangerously high, the independent safeguarding system steps in automatically to pop a physical relief valve or instantly shut down the chemical feed.
So the control narrative is the gas pedal, and the safeguarding memorandum is the emergency brake.
That is a perfect analogy. And the safeguarding memorandum is the critical document where you have to explicitly explain your logic. You can't just slap a brake on the car. You have to write down mathematically why you put it exactly there. You have to write, I put a pressure relief valve here, because if pump A ever fails, the pressure will spike to 50 bar within 10 seconds.
You have to prove it.
Yes, you have to rigorously prove your safety logic. The feed phase requires this formal justification for every single unit in the facility.
Which prevents people from quietly cutting corners on safety equipment just to save money or simplify the construction.
Correct. You have to put your entire safety philosophy on the official record.
Speaking of logic, we touched on it briefly, but the control narrative, the instrumented protection function narratives, and the cause and effect diagrams in this section really caught my eye. Cause and effect sounds a bit philosophical, almost metaphysical, but I assume in a feed document it's pretty literal.
It is extremely literal. It's essentially binary logic. The software layer. It's a massive, complex grid. Cause. Level in tank A reaches 90%. Effect. Pump B automatically stops. Cause. Fires detected by a sensor in zone 1. Effect. The emergency shutdown valve slams closed.
And all this software logic has to be written during the feed phase.
You definitely cannot figure out the software logic while you are actively pouring concrete.
Yeah.
You need to know exactly how the plant thinks before you build the physical body.
Yeah.
If you suddenly realize later that you need a brand new extra sensor to make your safety logic work, but you've already sealed the pipes and poured the steel reinforced floor,
You're in a lot of trouble.
they're bringing in jackhammers and ripping things up. It's a nightmare.
So we've designed the body, the pipes, the ergonomics, the tie-ins, and we've designed the brain, the control logic, and the safeguarding. But there's a whole other layer to this index that feels much more, I don't know, elemental. I'm looking at part 410, site preparation.
Right. The dirt work, getting the ground ready.
It lists geotechnical investigations, soil remediation, and even ecological measures to protect the local biology. This all goes back to really knowing your environment, right?
It does. You have to know exactly what is under your boots. Is the soil heavily contaminated from a factory that stood there 50 years ago? If it is, soil remediation means you legally have to clean the dirt before you can build anything. Yeah. Or maybe the soil is just soft clay that will slowly sink under the immense weight of a steel reactor. You need geotechnical engineers to calculate the exact bearing capacity.
But the real curveball for me, and honestly this is easily my favorite part of the entire deep dive today, was buried way down in part 6, site data.
I have a feeling you know exactly which one you found.
Section 6.1.4, archaeological investigation data.
Yes.
Archaeology. I mean, we are talking about high-tech refineries, massive modern power plants, state-of-the-art cause and effect control logic, and suddenly we have to worry about Indiana Jones showing up.
It sounds completely out of place in an engineering document, doesn't it? But imagine this very real scenario. You have fully mobilized 500 union workers. You have rented massive heavy lift cranes at $10,000 a single day. You have hundreds of millions of dollars in delicate equipment just sitting there on the dirt. You finally start digging the main foundation.
Okay, I'm picturing it.
And your excavator bucket hits a buried Roman wall, or an indigenous burial ground, or some protected historical artifact.
What actually happens? Do you just, carefully move it out of the way?
Absolutely not. By law, in almost every single jurisdiction on Earth, you have to halt construction immediately. You have to cordon off the entire area and bring in the government authorities. Your multi-billion-dollar project is now on total pause for 6 to 12 months, while archaeologists brush off pieces of ancient pottery with toothbrushes.
That sounds like a project manager's ultimate nightmare, just burning money every day.
It is the absolute worst-case scenario for a schedule. That is exactly why the FEED Index demands archaeological investigation data long before you ever sign the final construction contract. You need to know if there are ancient ruins down there, so you can either subtly move the plant layout or factor a massive delay into your financial model.
It's incredible. This dry, highly technical list is actually an attempt to predict the future. It's predicting earthquakes with seismic data, it's predicting massive storms with mediation data, explosions with hazardous area zones, and even the surprise discovery of ancient history.
That is the pure essence of FEED. It is a rigorous attempt to foresee every single variable, whether it's natural, man-made, or historical, that could possibly derail the project. You also see it in Part V with reference documents like the environmental impact study and dynamic simulations. It's all about predictive modeling.
There's one last aspect of these documents I want to highlight before we wrap up, and it's about the format itself. We've been talking all about the content, but in Source 1, the typical feed index, there's a really interesting note in Section 3 about an embedded Excel file.
Right. The PDF we are reading is really just a wrapper.
It says the actual usable index is an editable Excel file called typical findex.xlsx. And throughout the PDF document, we keep seeing those placeholders we mentioned, like insert bidder's logo and insert company logo.
That is a great reminder of the commercial reality of all this. This isn't just an academic textbook, it's a high-stakes transaction. The consultant takes this exact template, they open it up and customize it. In Excel, adding specific lines, deleting irrelevant ones, they stamp their corporate logo on the front, and they sell it to the employer for millions of dollars.
It's a stark reminder that mega engineering is fundamentally a business, and standardization using a reliable template like EA9 is totally key to keeping that business moving. You really don't want to reinvent the table of contents every single time you build a refinery.
Exactly. It ensures absolute consistency. When a massive global contractor sees document EA9, they know exactly what level of detail to expect, whether they are bidding to build in Texas, Tokyo, or Saudi Arabia. The format itself is a universal tool for communication.
So, zooming out for a second, we've gone from the core definition of feed to human ergonomics, safety logic, hazardous explosion zones, and even buried archaeology. For the listener out there, maybe they are listening to this on their commute or while doing the dishes, why should they care about document E4.1 or EA9?
Well, just look around you right now. The refined fuel in your car, the molded plastic in your dashboard, the continuous electricity charging your phone, the bulk fertilizer that grew the food you ate for dinner. Every single bit of it comes from massive facilities that started their life as documents exactly like these.
It's basically the hidden source code behind our entire physical infrastructure.
It really is. Without the extreme rigor of the feed phase, without forcing engineers to define the tie-ins and the seismic risks and the safeguarding logic up front, those facilities either wouldn't get built at all or they would be incredibly dangerous to live anywhere near.
It prevents absolute chaos.
It creates the mathematical and legal certainty required to invest billions of dollars. Banks simply do not lend money for good ideas. They lend money for completed feed packages that definitively prove the idea works.
You know, looking at this index today, I realized something. We usually think of engineering documents as instructions on how to build. Positive instructions, right? Like, do this, then do that. But this index feels fundamentally different.
How so?
It feels like a catalog of potential disasters. Think about it. Seismic data is only in there because earthquakes destroy buildings. Hazardous area classification is only there because invisible gas explodes. Archaeology is there because of project-killing delays. Ergonomics is there because humans panic and make errors.
That is a very perceptive way to look at it. The feed index is essentially a master list of everything that could possibly go wrong, meticulously turned into a plan to ensure it goes right. It is a roadmap through a minefield.
And if you miss just one line item, if you skip the safeguarding memorandum or you rush the soil remediation, the mine goes off. If this feed phase misses a single piece of critical data, like a hidden fault line or one protected historical artifact, an entire multi-billion-dollar project just halts.
The devil really is in the details. Or in this case, buried deep in the Excel index.
Well, I will certainly never look at a giant construction site the same way again. I'll just be driving by wondering if they remembered to do their archaeological scan.
Let's hope for everyone's sake they did.
Let's hope for everyone's sake they did.
Thanks for helping us decode the brain of the mega project today. It's been a genuinely fascinating trip through the paperwork that quietly powers the world.
My pleasure. It was great to be here.
And to everyone listening, next time you flip a light switch or fill up your gas tank, take a second to remember the thousands of pages of front-end engineering design and the invisible safety layers that made it possible. Thanks for diving in with us.
So curious.
We'll see you next time.
If you're interested in the templates, please visit our shop. The link is in the description.
Thanks for watching. Please subscribe and see next time.